Hello again, everyone. When we started Nextflow, we knew science was changing fast. But honestly, I don't think any of us could have predicted just how fast and how deep that change would go. This talk is really about that shift, how pipelines, infrastructure, AI, and collaboration are fusing into something completely new. We're going from pipelines to agents, and we believe that the future is so much closer than we often think. That's why I think this is the most exciting time to have ever been in the field, and I can't wait to see what's coming up the next few days. I'm going to start off today with the foundations. Whether you're doing greenfield R&D or manufacturing personalized medicines, scientific infrastructure is the plumbing of science. It needs to be flexible, but also scalable for efficiency and high throughput science. We need robustness to really handle those clinical applications. And increasingly, this infrastructure is what defines scientific innovation. ML and deep learning techniques are also transforming what's possible. We're in an era where having the right data and techniques can unlock a whole new class of insights. But in life science, copy-pasting general-purpose ML techniques won't work out of the box. Researchers need access to the right data, the right processing workflows, and high-quality models that are able to work in context. This data often needs to be relevant and ultimately build a continuous cycle of improvement through iteration. We'll explore how these tools and this cycle, this practical, repeatable cycle of science, can work. We're also going to discuss how Nextflow, along with the right data infrastructure, can enable that science. And thirdly, I want to talk about how this whole entire scientific research lifecycle is being reshaped. This is one that started with the digitalization of biology. It continued with the adoption of frameworks like Nextflow that use software like containers and cloud and source code management. And today, AI is pushing us into a new research paradigm. We're moving from often manual, serial experimentation to fast, iterative, massively parallel discovery. Scientists are being given the superpowers to move fast, to test quickly, and scale their ideas like never before. Bioinformatics itself as a discipline is changing too. We can leverage the advancements from software, but in a much meaningful way. The trend is more research moving in silico. More experiments with higher accuracy can be done upfront and then validated in the lab. Parallelization is becoming more relevant than ever, as it becomes really a key for scaling up experimentation. And then there's proliferation of new data types, new formats, really driven by powerful techniques, often in sequencing and imaging, that are expanding research possibilities, but also increasing some of the infrastructure complexities associated with them. And we're seeing how both individuals and institutions are building and then leveraging domain-specific ML models. As scientists, we've all seen how high-throughput sequencing changed our perspective of some of the fundamentals of biology. And as an industry, though, now it's our time to prove that the technology leads to more accurate targets, faster timelines, and does so more efficiently. We've always believed that better software leads to better science, and that purpose-built scientific infrastructure is needed for data-driven discovery. And many of you in the Nextflow community are not simply reacting to these changes. You're driving them. Seqera supports the builders and the scientists everywhere, often working with few resources on tough problems, but who work on what they do because it's the right thing to do. Many organizations have now joined us on the way. Our platform is now a critical part of the discovery engine for over 140 organizations. This includes thousands of scientists across the top 13 pharma, 17 diagnostics companies, and over 100 biotechs, including some of the most exciting names in the space. These teams are working across critical areas like discovery in rare disease, oncology development, clinical diagnostics, and they rely on Seqera to do better science faster, but with full reproducibility and while still being compliant. And Seqera really is the backbone of scientific discovery. I'm going to go through some examples of customers today and see some of the challenges that they've faced. Starting with Bio-Rad. Bio-Rad's a global company that develops, manufactures products for life sciences, both in research as well as clinical diagnostics. Provides instruments, software, consumables. If you've ever worked in a lab, you'll be more than familiar with it. What they were facing was a lot of pipeline sprawl. Scientists developing in different ways across many different repositories. They had slow turnaround times where analysis was really taking too long given the demand as it scaled. And they had rising cloud costs, inefficiencies that were being driven across the organization. This puts pressure on cloud costs and really needs to drive more efficiencies across. And they face complex tech hurdles. In clinical trials, genetic testing is really a key to biomarker discovery. And Sano, which is a UK-based startup, has built a research hub that accelerates the enrollment and makes research cheaper and faster. Does this by generating high-quality data sets and engaging with customers before and between research phases. To meet clinical trial deadlines, they were really struggling with scale-up, spending too much time maintaining data integrity, and they wanted to get that next level while ensuring excellence across the clinical-based processes. BioScribe is a leader in single-cell genomics, helps customers understand the heterogeneity, which drives a lot of development of diseases. This better understanding from cell-to-cell genetic variation is really critical for the development of more precise and effective treatments. Their challenges lied in the cost and the time of overheads, the complex data types for new single-cell techniques, as well as juggling cloud resources across their R&D efforts. And it was really through working with Seqera that each of them had seen such dramatic improvements and impacts on their business. Bio-Rad now has Nextflow as their platform, purpose-built for life science, that brings all of this together. Workflows to compute to data, everything managed in one place. At Sano, they built their genetic testing with Nextflow and Seqera. They made it automated, reproducible, and scaled the infrastructure. It's not just faster, it's transformational, collapsing the timeline so that trials can get off the ground faster and get completed earlier. And BioScribe, they were able to reduce their cloud costs by 70% with Seqera, which enabled them to process thousands of samples per day and support dozens of customer requests simultaneously. We've worked with these customers to build a platform that brings together the building blocks of compute, of data, of containers. And in Seqera, you can explore data, rich metadata-driven interface, run pipelines with reproducibility, scaling, and collaboration built in, and also analyze results through the integration of tools and notebooks your teams already use. It's really one system built by scientists for scientists. And Seqera is fully integrated with Nextflow and accessible in many different ways, depending on how your team works. That's CLI, API, SDKs, or even in the UI. And it isn't just about enabling workflows. We're really powering the infrastructure for scientific computation. Seqera is built on the shoulders of Nextflow, but what shapes us most is what we learn from the community, from contributions, from the thousands of scientists building pipelines, for teams that are navigating compliance and cost, and from customers who are deploying at global scale with very stringent IT requirements. And we've built something that reflects that. It includes the orchestration across different clouds, different environments. It has governance and security built in. Seqera is really becoming the place where organizations that value science go to innovate and go to scale. And it is through those learnings that we've got our own perspective. We're building for fair science. It's findable, accessible, interoperable, and reproducible by design. Making development and R&D fast so that iterations can be made and where those same artifacts can scale into production. Everyone has their own bioinformatics tool. And with Seqera, these are unified tools on a common tech platform. This enables collaboration across teams. And we enable our customers to have audit-ready science from the get-go. It's really these core values which enable science to be prepared for the future. And when we think about what that future is, we've got a few ideas. We believe it's going to be a lower barrier of entry than ever. This includes getting started really quickly. It includes prototyping, quick experiments, vibe coding analysis that really becomes a real option. A lot of the data handling, the data wrangling, the YAML gymnastics, painfully manually creating sample sheets, something becomes really a thing of the past. And with AI, we can really use tools to make this whole process a whole lot simpler. We also see automation, very much driven by agentic means, will lead to 1,000 times more compute. Already in Seqera, we see over 95% of the workloads are executed in a programmatic way. And this ability to run not one, but maybe 100 iterations with different tools, different parameters across different data sets becomes much more common. And with all this, the additional compliance we built into research from the get-go, this will reduce a lot of the overhead associated with it. But most importantly, overall, AI is not going to replace science in this world. Scientific judgment really matters. And this is where the future is heading and is already happening. When we think about our mission, everything we do is towards it, about advancing science for everyone through software. And as part of that mission, we really want to talk to a few folks out in the community and learn more about what they're doing. First of all, we'll hear from Julia, who's really one of the most inspiring scientists that I've had the chance to work with, and who's going to give us a little bit of insight into her startup, AlloX. Julia, thanks so much for joining me today. Let's start with the basics. What is AlloX?
And thanks for having me, Evan. AlloX is a tech bio company with a high throughput experimental technology that allows us to systematically map proteins to identify allosteric switches, which have the ability to modulate protein function at a distance from the catalytic site or the functional site of the protein. We use genetic mutations as the chemical perturbation to understand basically protein biophysics, with a particular focus on intracellular protein-protein interactions. And it's with this information that then we design and develop novel small molecule allosteric modulators targeting those switches.
Very interesting. So you're basically probing the allosteric information to get these insights. Maybe you can share a little bit more about how you're using AI to drive the target identification, and then maybe more broadly across R&D.
Yeah, sure. As a young company, we have to move fast, right? So starting from early ideation, we use deep research tools and large language models to help us mine the literature and support our target prioritization efforts. But most importantly, we used AI to fit the thermodynamical models to the experimental data generated in our lab. This allows us to extract the key biophysical parameters underlying these mutation effects. And we also combine our data with AI-based structural predictions to achieve more accurate protein complex structure predictions, which directly fit into our discovery pipeline.
That's incredible. It really kind of speaks to a lot of the scientific value that can be generated and can be really added to with AI today. One thing I'd like to maybe pick up on there, you mentioned like some of the works on AlphaFold. Obviously, this is computationally expensive work. What do you think about the role of computation in respect to your R&D?
Yeah. Well, first, I think computation is essential for us. So our core technology is fundamentally a hybrid between experimental and computational approaches. And on top of that, at the speed and scale at which we now generate data, computation becomes the only way that we can run robust pipelines and complex machine learning models in a reliable fashion. So in fact, we have actually dedicated now a full-time role that precisely does that, ensuring this seamless integration between wet lab data and computational workflows.
And maybe taking a guess, but I think that's where Nextflow comes in.
Yeah, exactly. Nextflows give us the reproducibility and the structure we need for the computational pipelines, while Seqera platforms allows us to scale without the team getting stuck, dealing with the tech headaches or relying on the computational team. I think most importantly, it enables scientists to iterate quick, to stay focused on generating that scientific value and creative process.
Julia, this has been wonderful. I wish you all the very best for AlloX and looking forward to following your journey.
Thanks to you, Evan.
LOX is a perfect example of what happens when you combine scientific insight with the right tools. Whether it's a startup or a large biopharma, across R&D or clinical, these are really tough problems. And building the infrastructure to solve these problems is the foundation of what we do at Seqera. And pipelines is very much at the core of this. So let's talk about that, the everyday experience of running pipelines. When it comes down to it, you can build the most powerful workflow possible. But if it's impossible to use, to reuse, much of that value is lost. You'll notice today we've added now a new responsive UI. It works beautifully on large screens, on laptops, without hunting around for buttons or logs. We're also continuing to make the best place to run Nextflow even better. It starts with simplifying debugging without making troubleshooting much easier. And it extends to troubleshooting with AI. Users now have an Ask AI button. When something fails, Seqera AI gets instant context. This includes all the task level information, the scripts, task logs, as well as compute infrastructure. It's about making scientists' lives simpler, both for themselves and their teams. On the concept of simplifying life for your future self, let's talk about reproducibility. And going beyond what Nextflow provides, such as the commit, what parameters do you use, we wanted to extend this further to the broader pipeline context. Today, I'm excited to announce pipeline versioning. Every single launch in Seqera is now tied to a snapshotted version. This makes development and iteration in R&D really fast, while enabling the publishing of pipelines for broader use cases. You can publish specific versions and also create default versions of pipelines. Pipelines have always had the ability to use specific revisions of a Git commit. Now you can either choose a branch and pin it so that the commit always is used, even if someone commits to that same branch. Or you also have the ability here to use the latest version every time. Importantly, every launch of a pipeline with config or a parameter change now creates a draft version. This includes checksums so that you have confidence that nothing has changed. And these really act like fingerprints for every pipeline version. We also added custom schema. So using this Nextflow schema design, you can create launch forms with just the inputs that matter. You can take an NF core pipeline like the one shown here and really make it simple, exposing only a single option. It's no longer just the versioning of the Nextflow code. Pipeline versioning brings us enterprise-grade control and a new level of reproducibility to Seqera, ensuring every pipeline run is traceable and auditable. Just as important as pipeline management is user management and the permissions. You've got multiple teams with sensitive data, dozens of researchers across research and IT, and you need the control that maps to your organization. With fine-grained auth now, you can define custom roles that reflect your users. You have expanded what just you can do from view or launch or maintain and added these fine-grained permissions. We've rewritten every API so that it allows this granular level of permissioning. And it can be applied to any team, to any user, while being able to be adjusted in real time. It's built directly into the Seqera UI as well. So it's designed to make this compliance easier, but more importantly, make your teams work faster. Now let's talk about resilience. If you're using spot instances, and you probably should be, you know how painful it can be when they get reclaimed in the middle of a run. Changes in the spot market combined with long-running and expensive jobs can really mean headaches. We built Fusion snapshots in a way to create a lightweight, incremental snapshot that tracks your task execution state. If the instance dies, we spin up a new one and pick up the state of the tasks just where it left off. Best of all, though, it's all automatic. There's no manual checkpointing, no custom engineering, and it's fast, so your tasks can spin up even with the shortest of windows. This works today across AWS, Azure, and GCP, and it's available on Seqera Cloud. This part of the talk has been titled Scientific Infrastructure, and when we say that, we really mean infrastructure as code. With the Seqera Terraform provider, you can now provide every entity in Seqera as code. This includes pipelines, your buckets, data sets, compute environments, even workspaces and organizations. This means you can standardize how science is configured across different research groups and really make the onboarding and updates consistent everywhere. It also means faster testing and iteration. You can spin up new environments, validate configurations, and then roll them back or roll them out with repeatable, auditable workflows. And of course, this makes everything tracked and versioned. No more wondering changes across prod or staging. This is really how modern developer ops can be brought to scientific computing. And it really helps customers build platforms that scale with their work. Enabling customers with these features is key. And it's not just enterprise R&D, but also in the clinical setting. I recently caught up with Alex Belzer, he's from Boehringer Ingelheim, to really discuss more on this and get his perspective, both from inside biopharma and across the NF Core community. Well, Alex, it's great to have you here. Maybe for those who don't know, can you start with giving us a little bit of background about your role at Boehringer, as well as what you've been doing in the community?
Yeah, absolutely. I'm working at Boehringer Ingelheim for about 5 years now as a principal scientist in translational bioinformatics in experimental medicine. So working mostly on translational bioinformatics, clinical trial analysis across different clinical trials in oncology. Within the NF Core and Nextflow community, I've been co-founding and helping out, especially in the early phase of the NF Core project, together with Phil and several others, been shaping the project there, but I'm still contributing via external contributions to NF Core. And I'm also part of the steering committee at the moment at the NF Core community, also helping and still maintaining the NF Core relationships that I have.
Amazing. And I think it's a really interesting transition as well as kind of intersection. When we think about bioinformatics and pharma, often there's a lot of focus that goes into discovery. What do you think are some of the key aspects when you think about translation of bioinformatics, maybe that are often overlooked?
The key aspect there is that you're not so much really looking into the actual discovery phase. So that's the first part of the picture in total. But the second part in the translation phase, the focus is usually on different aspects of data analysis. So it's more important, for example, that you can repeatedly come to the same conclusions. It's more important that you can do reproducibly the same thing over and over again with a defined in and output. For example, you already know what you're looking for, but you want to prove that this is actually something that you can confirm. Also over time, given different trial settings, for example, you would like to confirm what you're finding, your early findings are actually in a preclinical phase, for example. You would like to confirm this now in a larger population, for example. And these type of analyses are often a bit different from what you would typically do in a preclinical setting in the discovery phase of bioinformatics analyses. So I think that's the key distinction there. Yeah.
Yeah. I guess as part of that, there must be aspects of compliance or regulatory aspects that you need to consider. Maybe you can talk us through a little bit of what you've been doing there, both in the community and at BI.
It really depends on what you're doing, what type of analysis you're performing there. There's parts of this that are purely exploratory, where you can really do a bit more freely what you want to do. And then there's obviously also parts that are actually going towards diagnostics, readouts that are really like decision-making readouts, for example, that you really would like to use for decision-making on a patient population. And in these cases, you have to be way more cautious in what you're doing. Way more cautious, meaning that regulatory aspects come into place, how you should do certain types of analysis on a high level. There's aspects on how to ensure that your software that you're using is actually following best practices, basically how things are done, that you can also prove that if you give a certain analysis pipeline to keep in the Nextflow kind of ecosystem, a certain input, that your expectation of your output is exactly, let's say, X. And that kind of relationship is something that you're not as focused on in a discovery phase than you are actually in such a translational setting. And in regulatory aspects, that's actually an absolute must. You have to follow these rules. You have to make sure that all your aspects that you're doing in clinical trial setting, where these regulatory GXP aspects come into place, are actually adhered to. So it's a lot of extra effort that currently goes into making sure that your pipelines follow these aspects, that they are actually developed in a fashion that allows also for checking that they are fully compliant with these aspects. So these type of topics are actually coming into place.
Awesome. So we're definitely seeing a lot more GXP work that's coming in from around Seqera as well as across the community. Are there aspects of Nextflow in particular that are helping with achieving GXP compliance or being GXP enabled?
I think a lot of the aspects that are already very well defined in the Nextflow language are actually helping a lot here. So reproducibility is a key aspect in Nextflow that helps a lot with that. You can containerize software dependencies that you're using. You can do security scans. You also have a large ecosystem in terms of community behind that. That also helps in having hundreds, if not thousands of eyes on software that is being actively used in such pipelines. This is also something that increases trust. And trust, I think, is one of the key aspects if you're working with such regulatory applicable pipeline analysis environments. So it's really important that you really have trust in what you're doing and that you can also build pipelines like that, for example, in a way that allow people from outside to check, okay, are they doing valid things? Are they actually something that you can trust in?
Yeah. And any particular changes that you see coming up or work that's been going on across the community, which is going to be really helping that advance?
I think a great thing is also that we have such a big community now around Nextflow in general, and of course being really large now and people building things for all different aspects of bioinformatics analysis that you can imagine, and even outside of that. So it's really cool to see also other areas growing there. What I like a lot is actually that there is also some special interest groups, for example, working on industry adoption of Nextflow. There's also the regulatory special interest group in NF Core that helps in kind of channeling these type of aspects into the NF Core community. A little bit less active at the moment, but we are intending to reactivate that a little bit more now over the next couple of months to ensure that also feedback from pharma companies like Boehringer, for example, is actually coming back to the community so that the community can also pick up topics that are currently maybe considered rather a gap in the tooling around Nextflow and NF Core to be available in the wider community. Then hopefully we also get back functional solutions or can help build these solutions together with the community. And that's, I think, something very beautiful, actually. It's not siloed anymore.
Yeah, absolutely. I think getting that industry feedback and contribution really can help sharpen a lot of the tools around that. Well, thanks so much, Alex, for sharing these insights. It's really valuable. Also appreciate all the work that you've been doing around the community and sharing with us today.
Thank you, Kevin.
Machine learning and deep learning techniques on ever-expanding data types are transforming what is possible in life science. It's honestly wild how fast things are moving. We're seeing an explosion in the types of biological data being generated, whether it's a single cell, spatial, long reads, epigenetics, proteomics, metagenomics, and it isn't slowing down anytime soon. Each of these data types has its own formats, its own tools, and processing requirements. You really do need flexible infrastructure that can keep up. And if we look at the community and what's happening out there, NF Core is spinning up new pipelines faster than ever. Here's a collection of some of the ones that have just come out in the last year. And each of these solves a really specific analysis with very specific data types. It's really a great signal. Science is diversifying, and this community is certainly keeping up with it. We also need to consider, though, where that data is being stored. Over the last decade, most data and data science pipelines have standardized on a few common places: object storage, your buckets in the cloud, file systems, and occasionally places like LIMS or ELNs. These were the usual files that were centralized, predictable. Most often they lived in traditional IT-managed buckets or on-prem file systems. And while this gave us a lot of control, it also created a lot of silos, manual processes, and somewhat of a disconnect between experiment and the analysis. Today, with different data types, the adoption of different data management systems, things are starting to look a little different. We still have the object storage and the file systems, but now we're seeing a surge in dynamic cloud-native platforms. We're seeing scientific data being generated and stored in tools like Benchling across the wet lab, and Hugging Face for models, or Databricks and Snowflakes for large-scale analytics. As pipelines have become a critical infrastructure, the data that's flowing in and out of them can really come from anywhere, which means these scientific platforms now must adapt to that new reality. And if data can come from anywhere, how do we actually know where it's been? How was it created? Who ran it? This is really where Nextflow data lineage has become critical. We released this earlier this year and built it directly into Nextflow. You can trace every file, every intermediate file, final processes, all the way back to a specific run, a task, and even a specific parameter that was used. That's essential where data is no longer centralized, where pipelines are touching across many different sources. You can expect this data via the Nextflow CLI. And the really nice thing about this is it's all ID-based, meaning you can reference any file and get its full provenance from that ID. This, in a way, gives us a transparent, tamper-proof chain of custody to our bioinformatics. And within Seqera, we're also continuing to add new data integrations. Data Explorer can now connect to any S3-compatible object store. This makes finding data for your pipelines or your studios from really any other cloud or on-prem storage system much more effortless. This includes the likes of Cloudflare's R2, of Oracle Cloud, and Mini.io. The process for this is super simple, as you can see in the screenshot. Here we're using Cloudflare as an example, and really from the workspace credentials, we can go and add the credentials, and then from the R2 dashboard, simply create an API key with the right read-write access, paste in that key along with some secrets, and that's it. The data is now discoverable and previewable inside of Data Explorer. You can now browse it, download it, use it to start a pipeline. This unlocks a huge range of environments that goes outside and beyond the three main clouds. It gives researchers who are on clusters or those with hybrid cloud solutions support for Seqera out of the box. And Data Explorer isn't just for browsing files anymore. We see it as becoming a rich scientific interface. You can visualize directly in the UI, like this example here of a 3D protein structure viewer. No extra tools, don't need to switch tabs, just click and go. Here you can see you can view the structure in 3D, inspect the metadata, which is coming from the PDB, as well as any UniProt IDs, and share that with collaborators right in Seqera. And really see this as just the start. We're building out even more domain-specific visualizations for any data type that scientists would be working on every day. This is exploring FastQ quality metrics, to imaging data, to understanding what's taking place inside of models. It becomes the lens through which you can see and understand your science. Another key part of Data Explorer has been data sets. This is one of the most fundamental building blocks of how Nextflow pipelines work every day. Most of you are already familiar with sample sheets using CSV files that describe your inputs, describe samples, metadata, file names, basically everything your pipeline needs to kick off. But as the number of pipelines and experiments grow, managing these data sets can become a real pain. We're really trying to make data sets a core feature. And so with this, we're releasing the first in a series of updates to data sets. You'll see what's going on in this first case. We can now filter, search for data sets by metadata, keywords. Within one click, we can also see all of the runs that was used by a particular data set. You'll also be able to add labels to filter and add support for visibility. So it makes it possible to hide data sets that you're no longer using. We've also introduced new filtering options, so you can sort by things like username or labels, or even recency to find data sets where they were first used or where they were last used. And finally, we've updated the dataset's versioning functionality. This means that you can update a dataset while still tracking which version was used in a particular run. And it's really this kind of flexibility of your experiments, the ability to keep a record of something while still being able to iterate, that really makes the running of pipelines and the rerunning of pipelines really possible. Now on to machine learning. Machine learning and deep learning are reshaping life science. But it's really their success depends on bridging two very different worlds. On the one side, we have ML and data scientists, typically working interactively, maybe through rapid experimentation and iteratively on model development. On the other hand, bioinformaticians, and particularly those with pipelines managing very large data sets, multi-step analysis pipelines, and really scalable compute that really is heterogeneous in its requirements. Their tooling needs differ, but in many ways their goals are aligned. How can we unlock insights from this complex data? We've seen a little bit over the last 12 months of how this is possible. Nextflow provides a common foundation where ML research and traditional bioinformatics can meet. And then it provides that reproducibility, scalability, and infrastructure needs for the bio-ML world. To give some perspective here, AlphaFold 2 had 93 million parameters, while there were 405 billion in Llama 3.1. Life science models here, it's not about training the biggest LLM you can. In many ways, it's about success through crafting domain-specific solutions, built on data that's precise, relevant, and it comes along with a whole bunch of scientific knowledge. But we still need the right infrastructure, the data access, the compute, the reproducibility, that maybe you don't get from pure ML solutions. The best example of this is in single-cell biology. It's really something that sits at the intersection of bioinformatics and ML, typically dealing with tabular data in some cases that has a lot of biological context and meaning. I wanted to highlight one here in particular, openproblems.bio. Open Problems is a community-led benchmarking platform. They focused on single-cell methods. It was inspired by a lot of the ML success stories, things like ImageNet, where you can apply benchmarking models, in this case, to biology. Researchers are able to submit methods. These can be scripts, they can be notebooks, with the idea that those methods then solve real problems. Examples there you can find like denoising single-cell data, detecting cell-to-cell communication. And what I love about this is the community encourages the sharing of the data sets, of the methods, of the metrics, which really enables this true kind of apples-to-apples comparison that's taking place across these techniques. But what's most exciting from our perspective, Open Problems packages up all the methods, all the data processing, and makes it fully reproducible as a Nextflow pipeline. So they go from scripts, notebooks provided by any contributor, and they become part of a pipeline. These then run on AWS with Seqera, and all of the method contributions are automatically benchmarked. It supports the scalable execution, both GPUs and CPUs, to support a lot of the resource-intensive tasks like deep learning. And it's really with the modern infrastructure behind it that Open Problems is able to scale the community benchmarking to the global level. If you're curious about how this works, Rob Rick is going to be speaking at the conference later on, and he's going to be diving a lot deeper into the project later on. So please make sure you don't miss it. Notebooks are obviously a big part of ML, but equally too for bioinformaticians or computational biologists. We released Studios earlier this year to provide a Nextflow-like experience to interactive environments, one that included containers, one that could run in your own cloud. Today, we have a major upgrade that changes how interactive environments are created and managed in Seqera. Studios can now be configured and launched from a GitHub repository. This means your entire analysis environment, the software, the scripts, the configuration, can be stored as code, version controlled, and then reused by anyone. The benefit? No more manual setup, no more environment drift. Teams can really move faster with standardized and reproducible environments. Onboarding becomes a lot simpler. You can just point to a repo and everything's ready to go. It's the infrastructure as code model, but brought to interactive computing. And it's now live on Seqera Cloud. Let's walk through how this works in practice. You can now add a studio, paste in a URL of the Git repository that includes the environment. Seqera will then automatically pull that repository, reading the config, and build a container specifically for that. Once created, it's possible then to launch a studio, and we can see a live environment there which will be pre-configured with all the right tools and dependencies. By defining things like this in a repository, it works similar to Nextflow in that the environment is set up, reproducible, versioned, and collaborative by default. This brings a whole lot of consistency to how teams work and how analysis environments can be set up. So staying on the theme of ML and bioinformatics, earlier I spoke with Matisse, who's a postdoc at CRG. He's been working a lot with ML models, really to bring forward our understanding of single cells, and has been doing this as part of the Virtual Cell Challenge. Thanks for joining us, Matisse. Maybe you could give us a little bit on your background.
Okay, so I'm a postdoc at Cedric Notre Dame's lab at the CRG. My background is computer vision and deep learning, and I've been slowly transitioning into biology, which I've found like super interesting because there's a lot of very hard problems to tackle.
Awesome. Can you tell us a little bit more about the Virtual Cell Challenge?
So in the Virtual Cell Challenge, the idea is that if you have a cell, and in that cell, a gene malfunctions or being knocked down, its expression is like really low, what happens to the rest of the cell? So to solve this task, we are given a set of starting control cells and a bunch of cells where one single gene has been knocked down using CRISPR-I. Then we are tasked to predict the change on other cells, other genes in the cells, if another unseen genes will be knocked down. So that's kind of like a really hard problem.
And you've been using a lot of machine learning to solve this problem, as well as using Nextflow. Maybe you can elaborate a bit more on how Nextflow helps with these sorts of problems.
So the big advantage of Nextflow is the fact that it has a huge collection of modules that have been built by the community that we can then use out of the box. We're using the containerization and all these nice Nextflow features to essentially run as many pre-processing experiments as we want, and that really helps to kind of like iron out the artifacts, the biases, the pre-processing issues, explore the pre-processing parameters in an iterative way that usually gains a lot of performance.
When you think about the machine learning world and how that is really intersecting with biology now, what are you seeing in terms of how those worlds are colliding?
So I feel like machine learning, especially deep learning, is trying to develop in a parallel way to biology and especially bioinformatics. And oftentimes in deep learning, the way we process the data is just very different to the way it's done in bioinformatics. The deep learning field is still, in my eyes, lacking on all the knowledge on the pre-processing software that exists out there.
Now I want to zoom out and talk about what comes next. How do you operationalize all of this? One approach that we've seen is to use MLflow with Nextflow for production-ready pipelines. These can become used for training, for model deployment, and MLflow is a really great open source platform for managing the whole ML lifecycle. Everything from experiment tracking to model training can be deployed via REST API. What we've built here with our partners NebulaWorks is a framework that wraps all of that, and it also includes Nextflow's reproducibility and scalability. So data ingestion and pre-processing, whether this is coming from raw data lakes or databases, can really happen through standardized Nextflow pipelines. The feature engineering, the featureization can be done with Nextflow using kits like RDKit or Smiles encoders. And for model training, this can be handled through a Nextflow and ML integration. You can use popular libraries like scikit-learn or chemprop, and these models can then be deployed through these REST endpoints, fully orchestrated by Nextflow. This really enables this kind of direct use of ML within these research and development environments. It's an incredible example of how we can apply modern ML ops to bioprocessing and R&D. Up until now, we've seen how the foundations of science have been built on scientific infrastructure, how new techniques are pushing forward scientific innovation. But there's a bigger transformation underway. In this final part, I want to give a glimpse of how AI is not just accelerating research, but fundamentally changing how research is done. AI could be humanity's most important invention. This may sound like a bold claim, but increasingly it's becoming more difficult to argue with. Throughout history, we've invented tools that extend our physical reach, from the wheel to the rocket, but AI really extends our cognitive reach. It gives us ways to reason about complexity, to simulate possibilities, to generate new ideas, and even accelerate discovery. But I think what makes AI different is not just its power, but its ability to generate. It's not just a tool for executing instructions. It can reason, but also create, suggest, and optimize. And when we apply those capabilities to science, and especially to fields like biology, where the complexity is really the norm, it doesn't just speed up the research process, it can really reshape it. So the big question becomes, what can we do with this new power? At Seqera, we're not trying to build general purpose AI or chase the largest models. We're trying to focus our efforts where we can have an outsized impact. It is computational scientific analysis. With some of the most profound effects will come from the bench, they'll come from the sequencing core, and they'll come from the bioinformatics lab. That's why we've been building software that augments researchers with these superpowers. We want to give AI all the hard parts, having done the reproducibility, the scale, the complexity, so together we can solve these much bigger problems. From the moment you identify a promising target to the point you have a viable preclinical candidate, this is a process we all know can take 3 to 6 years. It's an incredibly complex process. While things have improved, it's still heavily reliant on manual, sequential steps in decision-making. The promise is that AI, with modern bioinformatics infrastructure, will shorten this dramatically. Maybe instead of 3 to 6 years, we can talk about compressing early-stage R&D down to months. Even if you think there's only a small chance that this becomes reality, and I admit there are many other big obstacles in the way, still believe it's worth doing. By applying AI across the computational work in R&D, and critically, by automating the infrastructure around it, the workflows, the data formatting, the deployment, biology has a chance to move at the speed of software. We believe this is a genuinely exciting scenario, and we're also starting to see it happen right now. While agentic AI using LLMs and tools is certainly a big piece of this, we also need those domain-specific, specialized models. AlphaFold 3 solved in many ways the protein folding problem, but it was solved through this diffusion-based generative model, not LLMs. But if we can use our reasoning capabilities, plus the large-scale automation, can really go far beyond predicting protein structures. Now, it's a very big vision indeed, but we need to take a step back and think, how can we build towards this? How can we make this happen? We need an integrated stack. We need a foundation which is built on scalable compute environments. We also need workflow orchestration and automation. This is really what Nextflow was built for, ensuring every process can run reproducibly, efficiently. We also need a data layer with scientific storage and metadata that's made discoverable and actionable. And finally, the components, pipelines, models, tools, studios. This is the software to run analysis and generate knowledge. And every layer here is critical. Really, on top of that, if we can build this foundational layer, the AI-driven scientific discovery becomes the next layer on top. And if you build this, we continue to ask, how can we enable this not just for machines, but for scientists as well? Exactly 1 year ago at Nextflow Summit in Barcelona, we unveiled to the community for the first time Seqera AI. And the response has been amazing. We've seen close to 200,000 chats, 12 billion tokens processed, and over 10,000 pipelines analyzed. But we're just getting started. This is just one piece of a scientific platform that revolutionizes discovery and can work to solve science's most difficult problems. So we've now launched Seqera AI V2, and it's available today on Seqera Cloud. And this version takes everything we've learned from the past year and levels it up dramatically. We're moving from not just answering questions now, but being able to action on them. Seqera AI connects directly into your workspace, so it has this full awareness of your responses, your pipelines, your computer environments. It understands data sets, can access workflow history, and even task-level metadata. This allows it to not just generate this general advice, but to be able to debug errors in your exact context, help create valid sample sheets for your pipelines, and really to even kick off runs directly. This all happens via natural language, and it's really this AI which is in the loop of your R&D. It's embedded into the fabric of bioinformatics and your pipeline development. You can ask Seqera AI even more specific questions. In this example here, I'm going to go through computer environments, but you can see it has access to all of the various entities in there. I'm going to ask a particular question about computer environment here, and you'll see it immediately understands the requests, can pull up the detailed meta information from AWS Batch here, can pull up the resources that are used. I can go deeper. I could ask questions about the resource usage, can see why tasks have failed, or even generate suggestions for a more optimal configuration. And because Seqera AI understands how pipelines interact with compute, you can even do things like create data sets and sample sheets, launch new pipelines. And it's really this context-aware AI agentic view that is really advancing how we can work with science. We're standing at the beginning of this era, where scientific resources are not just accessed by people, but also by agents. It's a shift from people-driven automation to systems that can reason and plan and act on behalf. And many of you in this room and in your organizations, you're using or you're thinking about that AI layer on the top. Some of you may have custom LLM applications. Some of you have internal co-pilots. But I hope by this point you've seen that how Seqera's foundation, how we'll be able to stack everything on top, is really what enables the full AI-driven discovery platform. So how can we build this and turn into real actions within the stack? Our vision of this is simple. We want agents to unlock scientific value, and we believe they must be able to connect to the core infrastructure of research, to data, to pipelines, to compute, to models. And to do this, we must connect agents across systems, no silos. We're going to let users interact how they want to interact, whether this is chat, things like VS Code or CLIs. We better keep AI secure as well. Runs within your infrastructure and runs safely. And we want to be able to bring your own models. So if you've trained your own LLM or you use one from the large providers like Anthropic, OpenAI, you can use whatever model you wish. And that's why today we're introducing Seqera MCP. It's our vision of making bioinformatics a first-class citizen in this agentic era. Seqera MCP is that layer which is able to tie together your compute, your pipelines, your data, your tools, and make them discoverable and also usable by agents. We think that with an MCP, we can make AI native science fair. It's a commitment to openness, commitment to standardization, and really trying to build a future where agents are real collaborators in that discovery. Seqera MCP is that bridge between your science and the agents. It's an AI layer that you may already be building, or if you're exploring internally. Now you can connect your workflows, pipelines, and make it all accessible from any AI system. Most importantly, it works today with any MCP-compatible tools. This includes if you chat with ChatGPT or Claude, if you use an IDE like VS Code or Cursor, or even if you use CLIs like Claude Code. It's also accessible by your own agentic frameworks. I'm going to show you here a real example using Claude Code, which is connected to the Seqera MCP server. You'll see what's happening is that I'm prompting Claude to add a pipeline to a specific workspace. And because it's connected to the MCP, it's able to collect all the relevant context, looks up which compute environments are available, verifies some of the metadata inside of that workspace, and it's able to, in a single flow then, add the pipeline, set the configuration, and launch it all on example data. This is real agentic bioinformatics in action. And this example is really just scratching the surface. The MCP has full platform API access, which includes 74 tools covering all of Seqera platform operations, workflows, computer environments, data sets, and more. The last year has shown not just incremental productivity gains, but scaling towards full transformative capabilities. We started using AI to solve questions, having knowledge-based questions like migrating from DSL1 to DSL2, or checking how a specific operator may work. We're now enabling complex actions, these ones that include more context, as well as actions to be able to execute, so fixing or rerunning a pipeline. And now with this foundation, we're going even further, one that can leverage AI for even larger problems. Being able to reproduce a specific paper on your selected data set. And there we start to shift from scientific tooling to be able to create scientific insight and drive scientific discovery. To make this vision real, though, we need one more thing, and that's you. Every major advancement we've seen, from NF Core pipelines to Nextflow plugins, came from the community. You've all contributed tools, created modules, shared open data. You've made your pipelines, you've made your publications more reproducible. This is really a collective momentum. And it's this flywheel of innovation. It really started here with this community. When we all contribute to science together, the impact really compounds. We want to make this even easier, make it easier for you to contribute. Whether you're building pipelines or developing plugins or writing tools, we want to reduce that friction at every step. Because the more seamless we can make that path, the faster that we can move, not just as an organization, but as a scientific community. And to support that, we're offering something tangible today. Everyone who signs up for Seqera Cloud with an organizational email now gets $100 of free compute. This is an execution environment ready to go. It means pipelines and sample data that are connected. You can run and explore immediately, no setup required. So whether you're a researcher or a bioinformatician or an AI agent, this is your launchpad. And this brings a close to the Nextflow Summit 2025 release. We've uncovered and really seen some exciting things in terms of pipeline versioning, studios as Git repositories, the ability to have supported features across data sets, and more integrations with Data Explorer, fine-grained permissions, as well as the new Seqera MCP. You'll hear more from other folks at Seqera across today and tomorrow. At 3:40, we have Geraldine, who's going to be giving updates from the community team. At 1 o'clock on Friday, Ben's going to be showcasing all the Nextflow-related news. And then at 4:20 on Friday, Phil's going to hold a talk to celebrate 10 years of multi-QC, the most commonly used open source tool for QC and bioinformatics. Thank you, everyone, for your time. Enjoy the talks and demos, and let's keep pushing the boundaries of scientific discovery.